That should be the case. And in this particular case, we are going to apply or emphasize on electrical circuit. Yeah. So our system that that will be of interest to see the effect. I mean, the application of Fourier series will be the electrical circuit. Yeah. Okay. So because we have learned electrical circuit before in your I think second year. I mean, sorry, first year, second semester, right? Electrical circuits topic. So I think the ideas of electrical circuit still there. Yeah, still fresh in your mind, I believe. Okay, so for us to calculate the response of these the response of a signal when the input to the circuit is periodic, there are two steps that need to be done. The first step is that you have to find the individual response with regard to each frequency component of the input signal. Okay, we're knowing that for periodic signal based on Fourier series, we have a few frequency components, right? Let's say we have omega naught, we have 2 omega naught, and we have 3 omega naught. For instance, we have 3 frequencies value, omega naught, 2 omega naught, and 3 omega naught. So what we have to do in the first step here is that for every frequency component, yeah, for omega naught, 2 omega naught, and 3 omega naught, we have to calculate the response with regard to this frequency component. So means that for omega naught, we are going to have its response. For 2 omega naught, we have its response. And for 3 omega naught, we have its response. So we are going to have 3 responses with regard to each input, yeah, each input frequency respectively. So that's what meant by the first step here, yeah, which is to find the individual response. Okay, then understood, yeah. Okay, number 2, once you have obtained these responses with regard to the frequency components, you need to add them together, yeah. You need to add them together to form the response signal. I mean, to form this Fourier series of the response signal. So the first step is to obtain the response with regard to each input frequencies. Number 2, the response that we have obtained from the first part will then need to be added to obtain the actual Fourier series of the response signal. Okay, so that should be the step that need to be taken. Yeah. So hopefully you understand what are the essence, yeah, the important informations with regard to this case, yeah, of the application of Fourier series in electrical circuits. Okay, so let's have a look at these examples here. We are given electrical circuits problem in which it's very simple circuit which consists of one capacitor, and we have the input voltage of Vt. Okay, so we are given that a Vt signal, a voltage input, is given by these equations here, where we have 3 terms. And we have 3 frequency components. If we base on these equations here, we have omega naught, we have 2 omega naught, and we have 3 omega naught. And each frequency component do have its own amplitude and phase as shown in these equations here. Yeah. Okay. So based on these input values, yeah, you need to calculate what is the current that flows in this circuit, which consists only a single capacitor. Okay, so that should be the questions, yeah? Okay, so this is where you have to adopt the steps that have been taught in the previous slide. Number 1, what you have to do is that you have to find out what is the response with regard to each frequency component. And yeah, that should be the first one. So based on this, we know that if we have 3 frequencies value, right? Omega naught, 2 omega naught, and 3 omega naught. So for every frequency values, we have to calculate the reactance of the capacitance, knowing that the capacitance reactance, which is Hc, equals to 1 over j omega c, yeah? 1 over j omega c. And for that, we are going to get for omega naught, it will be 1 over j omega naught c. For 2 omega naught, it will be 1 over j 2 omega naught c. And for 3 omega naught, it will be 1 over j 3 omega naught c. Because we have a different frequency components, yeah? So for every Xc that we have here, we can then calculate its current, yeah, respective current value, which is, for example, for omega naught, the current value will be simply the voltage over the reactance, which is given by this. Okay, so we have set to Vm over pi, cos omega t previously is minus 45 degrees, but since we have 1 over j omega c, which is divided by xc, so we're going to have omega naught c, and the phase now is changed to plus 45. Yeah, the phase now is changed to plus 45. So how we can get this? I think you have to go back to the basic of circuit theory. Yeah, since we have the division with the j omega naught c, so due to this effect of j, which is supposed to be negative 90 degrees, yeah, so Vt divided by Xc, so the result will be negative 90 will become positive 90, and plus negative 45, it will become positive 45. So that should be the first response when the frequency is omega naught. The same things apply for the second component, second frequency component of 2 omega naught. So with this reactance value, we divide the respective input. So this is your input, yeah, the Vt for 2 omega naught. So this value of input at 2 omega naught frequency will be then divided by Xc at this frequency. So we're going to have Vm over pi multiplied with 2 omega naught c, right? And because the phase is negative 90, so this will become negative 90 also. So negative 90 divided by negative 90, you're going to have 0. So there should be no phase, yeah, as a result of the cancellation. Okay, and finally, for the third frequencies, yeah, we have these terms here. Yeah, so set to Vm omega naught c divided by pi, so divided by 3 pi, and this will be divided by these terms here. And the phase, which is previously negative 135, will then becomes of negative 45 degrees. So once we have the response for each frequency component just now, the second step will be just an addition, yeah, addition of those response. So that should be, this will be the response of the addition of the response. Yeah. So what we have here is the addition of the responses. Yeah. This is the response from the first frequency. The second one is the response from the second frequency, and this is the response from the third frequency. So we add them together to give the final current flows in the circuit. Okay, any question for this example so far? Nope. So hopefully you understand, yeah, on these issues clearly, yeah, on how to apply the Fourier series in solving the case of electrical circuits, yeah. Right, so that should be the second problem. So I won't be covering these issues because it's similar to the previous example. The difference is that we are having another passive component, which is R here. Previously we have capacitance only, but now we have addition of R. So the changes will be on the impedance value. Yeah, impedance will be changes in which now the impedance will become R plus 1 over j omega c, and you're going to have this amplitude and phase component for the impedance. Yeah, so likewise the same things apply. Find the response for each frequency component, and once you have the response for each component, then you have to add them together to give the final current flow in the circuit. Yeah, right, so hopefully you understand these issues clearly. Yeah, so I won't be covering this, you can do this on your own. So let's have a look at this example here. Okay, we are given an input voltage for a circuit shown in this figure question 2c. The figure question 2c consists of two components of a resistor and inductor, both of 1 ohm and 100 respectively. The input VIT to the circuit is given by this 1 plus cos t plus 2 cos set of t minus pi over 4 volt. Okay, so based on this input voltage, you need to write the complex exponential form of Fourier series for the output voltage V0, in which V0 voltage is measured across the inductor L. Yeah, V0 T is the voltage measured across the inductor L of 1 Henry. Okay, so this is the case whereby we need to apply the Fourier series equation. Okay, so what you have to do now, first thing that you have to do is that you have to understand how many components exist in the input voltage here. So we have three components here. So the first component is a DC value, yeah, in which omega equals to 0. Second is when omega equals to 1. Yeah, this is for case omega equals to 1. For the third terms, this is for the case of omega equals to a set of 3. So for all value of omega that we have identified just now, you have to calculate what is the response or what is the V naught T measured across the inductor. So that should be the things that you have to do now. Yeah, I repeat, for every frequency value that we have, which include 1 cos T and 2 cos T minus pi over 4, for this term, you have to find out each response individually. Okay, so that's the first thing, yeah? And finally, once you have obtained the response, then only you add them together to give the final V naught T. Okay then, so let's have a look at the solutions. Remember, you need to find out the voltage across the inductor. Yeah? Okay, so let's have a look at the solutions for this example. Okay, so this will be the solutions then. So we have, this is the case, we are given the VIT and the output is here across the inductor 1 Henry. So to solve for the V naught T, you have to apply the voltage divider technique, yeah, voltage division technique, in which you are supposed to get V naught over J omega L shall be equals to VI over R plus J omega L. So the V naught T in terms of the VI shall be returned to be look like this. J omega L over R plus J omega L of VI. Okay, now we have three terms for the input voltage. The first one is at omega equals to 0. Yeah, so 1 here is for omega equals to 0. So for this case, by substituting omega equals to 0 in these equations here, we are now getting the V naught. The voltage across the inductor shall be equal to 0 volt. Okay, hopefully you understand. Yeah, you will just use this equation here, substituting 0 for the omega, and out we're going to have the V naught. The output will be 0. Then for the second case here, cos t is your omega equals to 1. So that should be omega equals to 1. So by substituting 1 into the omega in this equation, you are going to get J, omega equals to 1 Henry for the L, R equals to 1, and the rest will follow. And the VI will be the cos t, yeah, because at omega equals to 1, that should be your input voltage, which is cos t. So please substitute the cos t for the VI, yeah. So that should be the equations that shall be applied to calculate the V naught at omega equals to 1. So end up, you're going to get J over 1 plus J cos t, and this can be solved by using the Phasor form. So end up, you're going to get 1 over set of 2 cos t plus 45 degrees. Okay, so that should be the output voltage at omega equals to 1, yeah? So followed by this, you need to find out the output voltage across the inductor at the third terms, which is at omega equals to 3. So for these frequencies, your output voltage shall be J set of 3 times 1 plus J plus 1 plus J set of 3 times 1. And that should be the input voltage at omega equals to set of 3. Okay, so you're going to get this as the output voltage. Yeah, you're going to get this as the output voltage. So end up, you're going to get set of 3 divided by 2 of 30 degrees. The phase difference between these terms and these terms below here. And multiply with 2 cos set of t minus 45 degrees. So end up, you're going to get the answer for the output voltage at this frequency will be set of 3 cosine set of 3t minus 15 degrees. Okay, so you have now obtained the individual response with regard to the frequency component. So finally, to find the total output voltage, we just sum them together. So that should be the output voltage after the summation. Yeah, that should be the output voltage after the summation. Okay, then any question for this example? So hopefully by now you have understand clearly on solving, on applying the Fourier series in solving the electrical circuits problem, yeah, hopefully. Okay then. Okay, so let's proceed with these examples here. Again, we are dealing with the circuits problem. We are given RC circuit now. Just now it's RL circuit, so now it's an RC circuit. So the RC circuit is having a value of R of 1 ohm, a capacitor of 0.5 farad, yeah, and the input voltage XT for this given problems is 0.5 plus summation n from 1 to 3, which is only for odd value of n, and we have 2 over n pi cosine n pi t minus pi over 2. Okay, so this is the XT is given. So based on this, you have to, number one, find the Fourier series trigonometric cosine form of voltage Yt up to the third harmonics. It means up to n equals to 3. So what is Yt? Yt is the voltage across the capacitor C. Yeah, Yt is the voltage across the capacitor C. So this is the response that we need to record or need to calculate. Okay, and after that, the rest will follow, in which number 2, simply plot the spectrum for the Yt, and number 3, find the average power of Yt. Yeah, find the average power of Yt. Okay, so to answer 2 and 3, you need to find number 1 first. If you wrongly calculate number 1, so the rest will be wrong. Yeah, so please be careful on this. Okay, so let's have a look on the solutions for the Yt, which is solving the Fourier series, yeah, for the circuits here. Okay, so let's have a look at solutions. Okay, so please remember that we have these equations for this, this is continuation from previous equation just now, which is written in the trigonometric, exponential terms, yeah, so you can do it on your own. Okay, right, this is the one that we are going to discuss now. We are given the xt as shown here, okay, and we expand it further for n equals to 1 and n equals to 3. So this is what we are getting now, yeah, which is expansion of these terms here. Okay, so by using the voltage divider, we can write the equations that relate xt, yt, and the components value here. So we're going to have these equations here, yt equals to 1 over j omega c plus r plus 1 over j omega c multiplied with xt. So that should be your yt, yeah? The output voltage measured across the capacitor. And by simplifying these equations here, you're going to get this, which is 1 over 1 plus j omega c of r of xt. Yeah, so please try this. You're going to get these equations here. 1 over 1 plus j omega c r of xt. Okay. So now, from the equations here, we have 3 terms. The first one is for omega equals to 0. Second here is for omega equals to pi. And the third term here is for omega equals to 3 pi. So we are going to calculate the output Yt for respective frequency component. So let's start with the first one, which is omega equals to 0. So by substituting 0 in these equations, we are getting the Yt shall be equals to xt. Yeah, so when omega equals to 0, so Yt will be xt. So we're going to get the output Yt for the first frequency of 0 will be 0.5. Okay. Why 0.5? Because the DC, the value for the xt is 0.5. Yeah, that's the reason why. Okay, for the second frequency component, omega equals to pi. So that will be the case. Yt will be 1 over 1 plus j pi of 0.5 multiplied with 1. Yeah, because omega equals to pi, c is 0.5 and r equals to 1. So that should be the substitution of the omega, r, and c. And the xt will be at the omega equals to pi value, which is based on this, yeah, 2 over pi cos pi t minus pi over 2. That should be the case. So by solving this, you are going to get these equations here, yeah, 0.537 with the angle of negative 57.5 degrees, and multiply with this xt. So end up, you're going to get the Yt will be 0.342 of cosine of these frequencies and the phase angle, yeah? Okay, so that should be your omega equals to pi, the second output for these frequencies. And this will be then followed by the third terms, which is at 3 pi value. So we repeat the same technique, the same method, yeah, substituting omega equals to 3 pi, and this will be the input at 3 pi frequencies. So end up, you are going to get your output yt should be equals to this, yeah, 0.044 cos 3 pi t minus 168.02. So these are the output with respect to the frequencies component that you have in the problems, yeah. So finally, you have to add them together now. So when we add them together, that will be your yt output, which is the voltage across the capacitor of 0.55. Okay, so that should be your output voltage. Sorry, output voltage across the capacitor yt. Okay, any question for this? No. Okay, this is followed by this spectrum number 2. Yeah, since you have the yt. Yeah, we have the yt. You have the amplitude and the phase spectrum. But since the question asks us to just sketch the amplitude spectrum, so that should be the case. The spectrum 0.5 at 0, 0.342 at pi frequencies, and 0.044 at 2 pi frequencies. And finally, for the trigonometric cosine, yeah, since we have the yt is in trigonometric cosine, so the average power shall be based on this equation. So we have seen this in lecture 8 before, yeah, to calculate the average power for trigonometric cosine. So end up, your average power for the yt will be equals to this equation, yeah, 0.5, which is a0 squared, and the rest will be squared but divided by 2. So please calculate the average power for me. Thank you very much. Yeah. Okay, then that should be the solution for the examples. Let's have a look at if we have another examples to be done. Okay, so we have another examples now. So we are having this circuit. Yeah, we have this circuit with a voltage source of Vt. Okay, the Vt is given by this equation, 4 plus summation n from negative infinite to positive infinite of Cn exponential Jn 200 pi t with n not equals to 0 and Cn is given by this negative 8 over n pi squared, and the Cn is 0 for n even, means that what we're having here will be the Cn applicable only for odd value of n, yeah. And the circuit consists of 3 components. We have resistor of 2 ohm, we have resistor of 1 ohm, and we have inductor of 1 Henry. Okay, so based on this information, you need to write the complex exponential Fourier series expression of signal Vt up to the first harmonic. Yeah, write the complex exponential Fourier series for the Vt up to the first harmonic, means that up to n equals to 1. So it should start from negative 1 up to n equals to 1. Okay, so that should be the first case. So this is very simple question, which is just expand the Vt that we are having here. So just expand it and you're going to get the answer for that Vt. Number 2, you need to write the complex exponential Fourier series expression for what It. It is the current up to the first harmonic, means that you have to find the It. So to find the It, you need to solve for the circuits problem here. Okay, you need to find the It, you need to solve for the circuits problem here, which is solutions of the circuits problem in which the input is the Fourier series. Okay, same as what we did in the previous example. And number 3, once you have the It, you can calculate the average power as requested by these questions. Yeah. Okay. Hopefully you understand the questions clearly. Right. So let's have a look at the solutions for this example. Okay. Right, so we are having this figure, sorry, this is the case, right? So we are having these equations, and that should be your Cn without, mean that the Cn will be 0 for the even value of n, okay? Okay, so because the question asks us to find the complex exponential Fourier series up to the first harmonic, so that's why we have the Vt will be just extended or expanded from -1 to +1 of Cn. Yeah, so we're having these equations here. So that will be 4, this is 4 here, plus a -8 over pi squared, exponential -g 200 pi t, and followed by this. This is for n equals to -1, this is for n equals to 1. Okay, so that should be the answer for the first question. Okay, all right. And next one is to find the IT. So to find the IT, need to solve these circuits problems here. Yeah, so need to find the IT based on the equations of the components. So we know that from these equations, you have a case whereby the 2 ohm resistor is said to be parallel with the series summation of 1 Henry and 1 ohm impedance. Okay, so by right, you are going to get these equations to calculate the total resistance, and total resistance will be equals to 2 plus j 2 omega divided by 3 plus j omega. Okay, so straight away, this total resistance for this component will be substituted here, in which it shall be applied to calculate the current IT, in which IT shall be equals to Vt multiplied with this 3 plus j omega divided by 2 plus j of 2 omega. Okay, so hopefully you are clear about these issues. Yeah, it's nothing much here, just based on your understanding on the circuit theory previously learned in the last semesters. Okay, so from this equation, as what we have learned before, we need to substitute the frequencies component with respect to the input value. So we have 3 inputs now. We have at omega equal to 0, okay, at these frequencies and at these frequencies. So straight away we're going to get for 0 frequencies, we're going to get 3 over 2 times 4, okay, because omega will be 0, so we're going to have simply 6 ampere for 0 frequencies. For negative 200 pi frequencies, we're going to get this equation, which is substitution of omega by this value, and that should be based on the second terms of this, yeah, negative 8 over pi squared exponential negative g 200 pi t, so that should be the case. Okay, so multiplication of these will give us this equation, and end up we're going to get negative 4 over pi squared exponential negative j 200 pi t. That should be for the first frequencies component. And then for the third frequency component, which is 200 pi, the same flow will be used. Okay, just substitute the omega of 200 pi for this equation. So we're going to get finally your IT will be 4 over pi squared exponential j 200 pi t. So end up your IT will be equals to this, yeah, in which we're going to combine them together. So 6 minus the value for n of -1 and the value for n equals to +1, yeah. So that will be the current in the circuit, right? And finally, for complex exponential Fourier series, okay, we just based on this IT, yeah, and since the IT is in complex exponential, you have to adopt the equations here to calculate the average power. Okay, so we're going to get average power will be 6 squared plus 2 multiplied with these coefficients of 4 over pi squared. Okay, so that will give us the average power of IT in watt. Okay, hopefully you understand about these issues of application of Fourier series in electrical circuits. Is there any questions on this lecture number 9? Any questions? No? Okay, so if there's no questions, so that should be the end of chapter 2. Yeah, so we have successfully learned the Fourier series. Okay, starting from the fundamental or introduction to Fourier series, what is the application of it, what is the benefit of Fourier series, followed by learning about the spectrum, learning about the type of Fourier series, and then we have learned about the method or theorem used to calculate the average power of the periodic signals. And finally, we have learned how to apply the Fourier series in solving the electrical circuits problem. So next lecture, that will be starting next week. Yeah? We are going to cover the chapter 3, which will be on Fourier transform. Okay then, any questions for this lecture 9?